Next, we'll consider the structure of the interior of the sun. The sun, we'll draw it, the Earth we drew as a vertical diagram, but following the conventions of the Earth and atmospheric community. But for the sun, we're going to draw this as a radial diagram horizontally. So this time, the horizontal direction will be radius, starting from the center of the sun and working our way outwards. Our vertical axis this time will be the temperature of the sun. And we're going to start from the beginning, or we're going to start from the middle of the sun. And we're going to do the temperature in a log scale because the temperatures in the sun are quite extreme. The temperature at the very middle of the sun it's quite hot, and it's about 15 million degrees Kelvin. In the interior of the sun, it's quite hot. That's temperature that's sustained by nuclear burning. And then as we move outwards in the sun, that temperature decreases. In the inner roughly 10 to 20%, we call that the core. This is where the actual nuclear fusion occurs, which we'll denote with an epsilon nuke. So this is the generation of energy from collision of protons to create helium. So H goes to He and releases quite a bit of energy. And then that energy is carried outwards by radiative transport by photons in what is called the radiative zone of the sun, the zone where photons carry the heat. As we move outwards in the sun, and as the sun gets cooler and cooler and cooler, eventually the sun gets to be a cold enough plasma that the plasma becomes more opaque to the photons within it. And then the temperature gradient steepens to carry the energy out, and this becomes steep enough that we get large-scale motions. And this is called the convection zone of the sun. We get large-scale thermal instabilities of convection. In terms of the proportional radius, the radiative zone occupies roughly the inner 70%, 0.7 solar radii. And the convection zone reaches all the way up to the photosphere of the sun at 1 solar radius. Here is our photosphere. And the surface of the sun is vigorously convecting. We've gone from a temperature of about 15 million to a temperature of roughly 6,000 degrees Kelvin. So we've gone from millions of degrees to thousands of degrees. And at this point, photons start carrying the energy again as the sun becomes transparent. Okay, now what happens above this point? What happens in the outer parts of the sun? Well, let's get ourselves a little bit of space here, because something quite interesting happens, and it happens quite quickly. So we're gonna get ourselves some space, and we're gonna break our axis here so that we can change our scale and draw things on a vastly different scale. Before we do so, the sun is about 700 million meters, megameters in radius. The solar convection zone is about 200 of these megameters, and this is just a convenient unit of measurement. The convective patterns at the surface of the sun are about 1 megameter. All right. Now, above the surface of the sun, what happens? So we're gonna break our scale here and zoom in, and we're gonna consider things on sort of a distance of a couple of megameters. So very zoomed in distance. Well, the temperature at 6,000 degrees, it drops a little bit more to the temperature minimum of the sun at about 3,000 degrees. It's actually cold enough here that we see molecules like carbon monoxide, whereas down here we have fully ionized hydrogen and electrons and fully ionized helium. At the surface of the sun, we start forming exotic H minus molecules. So this is a hydrogen atom with an electron attached to it, a second electron. And we come up and we have carbon monoxide and all sorts of interesting things in the lower atmosphere of the sun. Now, as we continue out in the sun, something strange happens. It actually starts to get hotter. And it gets hotter to about, say, 10,000 degrees, a few 10,000 degrees here in the chromosphere of the sun. And this is where we see pink light during eclipses. Then it actually gets quite a bit hotter. It goes through what's called the transition zone of the sun. And after we've gone through several 100,000 degrees, we get up to the corona. And the corona continues on out. And the corona is at temperatures of 1 to roughly 4 million degrees Kelvin. So on a similar scale to the core of the sun. Now I've drawn it a little extreme given the actual temperature at the core of the sun that I drew. So let's rescale this a little bit and make it slightly more in keeping with our temperature scale. So the corona here is at about 1 to 4 million degrees Kelvin, and this is the corona. And as we learned, the corona is not a hydrostatic object. There is a flow outwards of the solar wind. So this is our sun. This transition from atmosphere to chromosphere to corona, this happens within a few megameres, or less than about a percent of a solar radius, or a few percent of a solar radius. And then the corona, it continues out for quite some ways, roughly 10 or so solar radii is the corona of the sun. And after that, after about 10 solar radii, you transition into the free streaming solar wind because you hit what's called the co-rotation radius. Where the sun rotates so quickly that Alfvén waves on the magnetic field of the sun can't keep up with the motion of the plasma. That's not because the sun itself per se spins quickly. It's that the sun spins quickly enough and you're at now a far enough lever arm distance out that the plasma here is moving faster than magnetic Alfvén waves can keep up with. And so we switch kind of out here into the free streaming solar wind, in which our Earth is embedded at a distance of about 200 solar radii. So again, going from the outside of the sun to the outside of the sun is quite hot, several million degrees Kelvin in the corona. As we come deeper into the sun, deeper into the atmosphere, it cools down to the chromosphere and then the temperature minimum here. We hit the photosphere of the sun at about 6,000 degrees Kelvin. And then as we go inside the sun gets hotter and hotter. It very quickly, very close to the photosphere, ionizes into hydrogen and helium plasma primarily. And as we go deep in the sun, we first have a convection zone with large-scale fluid motions carrying the heat in convective instabilities, and then deeper down, a radiative zone where photons carry the heat, until we reach, at the center, the nuclear burning core, which occupies the inner 5 to 10% or so of the sun for its substantial energy generation.